particularly a research talk. So this talk is about load balancing, WB, and is joint work with Diego Goldstein, who is a postdoc now in Uruguay, who returned to Uruguay recently and joined our group. He's a former master student of our group that went to Eindhoven to study with Sembos. Then he spent some time at India with post-geographic, and now he returned. And in particular, Diego received the second prize as in Sigmetrics as the second best PhD thesis for his thesis recently. So it's very, very strong. And most of these results are his. I mean, just try to organize them in a way that's easy to follow, not that easy. I will try to do my best. Okay. So what are these stochastic processing networks and what is limited connectivity? So this is what I want to discuss today. So let's start by stochastic processing networks. What I mean by that? What I mean is load balancing in a very general setting. So load balancing, we all know, plays a central role in parallel processing systems, particularly in the cloud. How to route things to servers very efficiently and balance across all the servers, all the capacity you have, and has received, of course, a lot of attention in recent decades. For instance, if you want to follow the literature, there's a very nice survey by Mark van der Voort, and it's here somewhere. That's Mark van der Voort, Sam Bors, Johan Vallevarden, and Banco Mukerki about all the recent literature on the subject. Okay, so the main goal of this load balancing is to achieve what we say is complete resource pooling. It's like the system behaves as a single server queue for everybody. Okay, so nobody notices that there is a load balancer balancing things across a network. We think of the system, we perceive the system as a single server queue. But it also needs to be scalable. So you cannot do it whatever you want because the number of servers is very, very high. Okay? So the first load balancing model in this scenario was called the supermarket model, a few decades now. It's a simple load balancing when you have a dispatcher, which is the gross, that has to balance tasks, exponential tasks across servers. Each server maintains its own queue. And we make the arrival rate n lambda and have n servers. So the load on the system is lambda over mu. And the important thing is tasks are queued at the servers. Okay. So what's the optimal policy here? Everything is exponential, and you are not allowed to queue at the dispatcher. You have to dispatch immediately. Then it's showing the shortest queue. Everything is symmetric. So you're showing the shortest queue among all of them. This is the optimal policy, and achieve this pooling for large n. So you don't see any idleness in the system. You don't lose efficiency for large n. But it involves a large communication overhead because you have to know the state of all the queues in your system, and n is large. So the dispatcher has to have a lot of information. So people started to come up with other type of policies, and the most popular one was power of D, which is maybe you know it. Just to recall, is choose D queues at random if D greater than 1. So instead of choosing one queue at random, choose 2 or 3 queues and route to the shortest among these samples. Okay. And this provides a doubly exponential decay in the occupation of the system. So if you do random routing, you get geometric decay. This is doubly geometric or doubly exponential, where it's a lot faster, so the system performs more efficiently. If you do this simple choose at random 2 and then go to the shortest. Okay. And then there's another policy that's very popular. I won't cover that today, which is join the idle queue, which is upon arrival, just choose an idle queue. And you have to trust me that you'll find one. Okay. So in fact, this works particularly if your load is not high. Okay. So it's rho over, no, it's rho over, not over, and it's rho far away from one. Okay, so it's if rho is far away from one, there will be idle queues in the system. So you just have to keep track of them. How many idle queues are in the system, and this requires less information. And when tasks arrive, it's highly likely that they find an idle queue. Okay, so you don't use efficiency. So this is the most popular in terms of trade-off between efficiency and the communication output. Okay? But the problem is that networks are complex, are not as simple as we want them to be. They have multiple entry points, types of tasks, heterogeneous servers, and in particular, something that is very important now is what we call compatibility constraint. Is that not every dispatcher or type of task can be routed to any server. The server has to be prepared for that task. For instance, in machine learning inference, the model has to be loaded before. If you want to do some analysis on some data, the data must be on the server, and not all the servers have all the data. Or maybe a geographic thing. So you want to route to servers that are close by because of latency. So you have some compatibility constraints. This is just a random graph, but the right abstraction for this system is to think of it as a bipartite graph. Okay. So for me, a stochastic processing network will be a bipartite graph with dispatchers on one side, servers on the other side, and edges that connect them and tell me which dispatchers, which tasks can be sent to any server. Okay. The servers execute tasks sequentially as before at some rate, mu that depends on the server, and the dispatchers receive tasks at some rate, lambda, that depends on the server. Okay. And we will assume in what follows that we will use trying the shortest queue, which would be the optimal policy. And the reason for that is that we are looking for lower bounds on performance. So if you lower bound the performance of the optimal policy, then you have a lower bound for all the other ones. Okay. So I will focus on showing the shortest queue. And I call the stochastic processing network is the process that keeps track of the number of tasks or the size of the queues in each server at time t for a given bipartite graph and arrival rate functions and service rate. Okay, you have bipartite graph, arrivals, departures queues, keep track of all the queues, and the important thing is how well connected is this graph. How many choices dispatchers have in order to route things across servers. This is the key point. Okay. Of course, you need this process to be stable. This is a macro process because everything is exponential. You want it to be stable, and the stability condition is well known. In fact, it comes from a paper by Sergei Foss. It is sufficient for the system to be stable that for any subset of servers that you choose, you look at the nodes and the dispatchers that can only send traffic to those servers. Okay, that's the idea. And they are required to send traffic to those servers. So the number of the arrival rate of those dispatchers should be less than the capacity of these servers. Okay. But this is for all sets. It's complex to verify. And we will assume that we are in an ergodic process. Sometimes it's easy, like in the simple network I will show you later. But it's a complex because mainly across all subsets of servers. Okay. And by n of d, the neighborhood of some dispatcher. Okay. So the possible servers that he may send traffic to. And so I will assume stability and define x, not in boldface, capital X, as the steady state of this one. So the steady state number of people in the queue in server U at which is a random variable, a random vector in the steady state. Okay, the steady state of an macro process. So the simple processing network that will be key to our proofs is exactly the supermacro. So it's a bipartite graph with one dispatcher, capital S servers in our new notation, and it's complete. So the dispatcher can route things to any server. So the general definition contains the supermarket model, but I define the load a bit differently. I call the load here rho equal lambda over mu. So this will be ergodic if lambda over mu is less than the total number of steps. So this is better for generalization than what I wrote in the previous. Okay. And this will be the key to workers. Okay. Well, how do you keep track of performance in these systems? Well, this is an invention by Deng Skaya and Semacher for the supermarket model. Instead of looking at the queue in each server, okay, let's just look at how many, what's the fraction of servers that have more than I tasks at some point in time, or in state. Okay, this is in state. This is what we call the occupancy measure of the system. And so Q of 0 would be 1 because every server would have more than 0 tasks. Okay, Q of 1 is how many servers have more than 1 task, more than 2 tasks, more than 3 tasks. And you normalize by the total number of servers. So this is a probability distribution. That is a random variable, but it's a complementary CDF of a probability distribution in the interface. Okay. So what I want to say is lower values of Q imply that basically Q of 0 is equal to 1. In every stable system, Q of 1 is equal to the load. Okay. So what you want is Q of 2, Q of 3, Q of 4 to be as low as possible. Okay. Because you don't want servers to have more than 3, 4, 5 tasks. Or other way to think about it is the sum of all these random variables Q is the total number of tasks. So it's proportional to the total number of tasks in the system, and thus the delay by the system. Okay. So this will be the key measure for performance. And this is just a restatement of what I said before about load balancing. If you have a sequence of simple networks that grows in size without new notation, and you take the arrival rate also growing with the size, then you have a constant load in the new definition. And in the mean field limit, when you let the system grow, you get a mean field limit where Q concentrates around these 3 cases. If you do random routing, so you don't look at the queues, just pick one at random, this measured Q is just a geometric decay. But if you add 2 power of t, then you get a doubly exponential because it's 2 to a rho to the 2 to the I. A bit tricky to say. Okay, so this decays very fast. And in fact, if you do short the shortest Q in the midfield limit, you get Q of 1 equal rho, and the rest is 0. Okay, so this is still optimal in the fluid sense. Everybody has exactly 1 task, and nobody has 2 tasks, or 3 or 4. When you load balance, you find the shortest Q. This is in the fluid limit. Of course, there will be deviations from that in the stochastic system. Yeah.
Is there a proof of the exact shape of the double exponential in the beyond the midfield limit?
Not that I know of. It's a good question.
So it's a conjecture then.
And no, I mean, in the midfield limit, you concentrate around this.
Yeah.
So expected value of Q converges to this, and the whole process converges to this. But for finite size, I don't know. I mean, you have to control the tail somewhat in finite size. Okay, it would be interesting. I never thought of that. But, yeah. Everybody does this in the mean field limit. Okay,
yeah, but it's a caricature.
Well, I'll be happy with this talk because we will be talking about finite size systems. So
okay, very good.
So the talk is about finite. So the thing is, the simple network is fully flexible. Everybody can choose whatever they want. The problem is, can we have the same performance of the fully flexible system if we have less flexibility? And I will cite just one result of so you can see what type of results are out there about this. In this case, a result by Devanku Mukherjee, who was also a student of St. Borst, and he's now a professor at Georgia Tech, and he also received the Rising Star awards in metrics. So SEM is very good at generating great PhDs, I think. So what this is saying beyond the questions is that you have a sequence of graphs that is each one is larger than the other, and you have two measures associated with the graph. This is a regularity measure. So this will be basically 0 if all the nodes, all the dispatchers have the same number of choices. Okay. So a completely regular graph, of the same degree for everybody, this will be 0. So in some sense, this measures the variance of degrees of the dispatcher. And this is a measure of the mean degree of the dispatcher. It's inverse degree. It's a bit weird. I will relate this to the mean degree of dispatchers later on. Okay. So just say phi is a measure of irregularity. The greater phi is the graph is less regular. And gamma is an inflexibility metric. When gamma goes to 0, the average degree, the number of options grow. What they can prove is that if both of these metrics go to 0 in the limit, then the load balancing process of this bipartite graph works as well as the fully connected graph. Okay, so you get the same limit, even if the network is not connected. If in the limit it has enough options for the dispatchers, then you see the network as if it were a fully connected. Okay, a fully connected bipartite. This is the type of results that they have in this paper.
But there is something I missed for sure, because so if the networks are regular, if the regularity and the flexibility of the network goes to 0, then you have this nice property. You behave as a fully connected graph, but there is nothing that imposes some connectivity. I mean, I can be regular and have just one connection. So maybe it's this one.
That's the other one.
That is, so flexibility is the connectivity.
Flexibility is the connectivity, exactly.
So
Since they use inverse degree,
okay,
the greater your degree is, the lower is gamma.
Okay, so that is inflexibility.
That's why I call this inflexibility.
Or inconnectivity. Okay. Or unconnectivity, let's say. Okay.
This or unconnectivity. Yeah, exactly. Yeah. So you need both of them to go to 0 in order to have. So you have to be regular. Your dispatches must look the same or almost the same in terms of degree, and also you have to have many options. So this is what it says. Okay. This paper that I quote is for power of T, and it's the most well known. It's very recent, but similar results hold for other policies as well. And this is a note that, in particular, gamma going to 0 implies that the average degree of dispatchers have to go to infinity. Okay, so you need full flexibility. It's related to your question. Okay. So what I want to do, and it's already very late to talk about what I want to do. The introduction was very long, but what we look is for converse results. In particular, we want to know when you cannot get rid of the geometric behavior. Okay, so if you have good connectivity, then you will have a fast decay on your occupancy measure. So what's necessary for that? Okay, when you lose that, what are the metrics that tell you you don't have this behavior, you still have a geometric behavior? So we provide a geometric lower bounds for the new behavior when connectivity is limited, so the opposite. Okay, and we introduce another bottleneck measure that we use, as well as the average degree. So you need both, again, two metrics. And we show that unless these metrics diverge, there will always be a geometric tail, even under showing the shortest. Okay, so our metrics are, on the other hand, have to go to infinity, not to 0, but the idea is the same. You have to, if you don't have enough flexibility, if you don't have enough connectivity, then you will find some part in the network that will stay working as a geometric cube. Okay, that's the reason. So what are metrics? Well, given a bipartite graph, I think this is a very nice idea by Diego. He proposed to use this bottleneck metric. He doesn't like the name. I named it bottleneck metric because it's, if you look at the mean there, you fix a server U and you look at the degree of the dispatchers that are connected to you. And you take the mean of that, the minimum of those. So if this minimum is low, that means that this server is really important. Okay? Because the degree must be at least one, you must be connected to one server. But if the degree is true, then this server is one of them, and it has only one other option. Okay? That's the idea. So the lower the mean degree you are, the more important this server is. Then you average that over all the mean. Okay? So this magnitude measures how important this server is for some nodes. So this is a metric of average importance of the server. Okay? Or how many bottlenecks you may have. So if some dispatchers have only two options, then the subset of servers that serve them may become a bottleneck for the net. Okay? Congestion will occur there. And if the size of this subset grows with the number of nodes, number of servers, then you're in trouble because the size of the set that is congested is growing. So you'll never get a complete resource pooling. The other metric that we use is average degree as a measure of flexibility because it's simpler than the gamma that I showed before. And in fact, using Jensen's inequality, you can show that gamma going to 0 implies beta going to 0. Okay, so it's a bit weaker than gamma in some sense, but they move in the right direction. And why both metrics are necessary, let's look at some examples. So these are a processing network that has two sides. On the left side, it's fully connected. So this side will work particularly well, no problem. But on this side, you have one dispatcher that has only one server. So this server becomes really important for this dispatcher. That's the idea. And you can never have other than geometric tails here because you have MM1 queue on this side. So one dispatcher with no options is an MM1 queue. And you have a bunch of them, you have N of them. Half of your dispatchers are MM1 queues. So the system won't perform as well as there are not many options. Okay. And this is controlled by the alpha, but the average node degree grows because the other side of the network is fully flexible. So I think this is a nice example. So if you don't control that, there are some nodes that have few options. Some nodes, and these nodes are a large portion of the network, then you have to control that in some way, and the alpha does that. The other example is a bit, I don't like this example, but it's in the paper. You have two networks here, so you are treating a bit the system. The left side of the network is obviously N MM1 queues in parallel, one dispatcher, one server. So this will behave bad, okay? But the alpha is treated by the other side of the network because the average degree of the other dispatcher is the minimum degree of the other dispatcher is large. So when you average, you get alpha going to 50. But the average degree of the nodes remains bounded. So in this case, you need beta control to show that this network is bound. Okay. So sometimes it's alpha that governs our bounds, sometimes it's beta. That's the thing. So what are our results on this? Okay, so first a lemma for finite size networks from Francois' topic. Assume that you have a simple and ergodic load balancing process. So you have a supermarket mode, capital S queues in parallel, one dispatcher. Then in steady state, the average occupancy will have a geometric tail. Okay? So for finite size, you will always have geometric tails. Even one dispatcher and full connected. Of course, the rate at which this tail goes to zero, or the ratio of the geometric decay, is very fast when S is large. That's true, because you have many options that you have to converge to the showing the shortest tube fluid mean field where everything goes to zero. So this rate here has capital S to the capital S times I, if you plug in this function in there. So it's really fast. It's really fast, but still geometric. So this bound will tell you that for finite size systems, you get a geometric behavior. And what we will do in the proofs is to try to generalize these to networks. And if you can decompose the network in things that do not grow, that remain finite in some sense, then you will have geometric decay. That's the idea of the result. Okay. So every simple network has a geometric tail for finite S. And we do this by coupling with single Sarri Q. It's a really simple, straightforward proof. So this system, if you couple it with the same probability, in the same probability space, in the same arrival process, will always have more customers than this system. The idea, where you put all your capacity in one server. This is well known, multiplexing. So the total number of customers even in transient, not only in steady state, in the left-hand side is greater than the total number of customers in the completely full system. So X is ergodic by assumption, then Y would be ergodic because this is a stability condition for the MM1 system on the right-hand side. And in steady state, the probability that there are more than I customers in the left-hand side system is greater than the probability that there are more than I customers in the right-hand side system. Okay. So this performs better. I mean, what we need are this type of probabilities, but with the probability inside, I'll show you. So I need to estimate this because I want to control expectation of Q, which is the expectation of the sum over I of all of this. So I need to compute this. In order to compute this, I need to compute this, the probability of X greater than Y. And in order to do that, we do this bound, which seems pretty loose, but it's not that loose. Okay. Consider the system completely full, the single server system. The probability that has more than capital S I customers is less than the probability that the load balancing system has more than capital S I customers because of the monotonicity. And for that to happen, at least one of the Qs has to have more than I customers. Okay. Otherwise, the sum will be less than capital S times I. And then we use the union bound. Just sum all of these probabilities will be larger than that. Since all servers are equally distributed, these probabilities are the same, so you get this bound. Okay. So the only thing loose in this bound, this seems pretty loose, but the only thing really loose in this bound is the last one. The union, the capital S in the last step. The other things are pretty tight if you look at the space statements. Okay. So you cannot get much better than this, except for this capital S term. No, you can relate the probability that any server is occupied more than I with the probability that the MM1 server is occupied, its occupancy is larger than capital S I. Okay. So to compute this expectation, I need this a probability. This probability is greater than capital S on the other side. And this is an M1Q, so I plug in the probability that the M1Q is greater than capital S times. What I was saying before is that the only thing that is not very tight here is this term. All the rest you need pretty much. So I would like to get rid of this term, some other way of doing the result or something. Okay. So how this relates to the alpha and the beta that I defined before? Well, okay, this tells you that this does not depend on you, on the server. So if you average over all the servers now, sum and compute the expectation of QI, then it will be greater than this, because this does not depend on the server, the same one for all servers. And it has the size of the system here. Well, in the simple load balancing network, our metrics alpha and beta are exactly the size of the system. So we can restate this, okay, as the expectation of QI is greater than this. That's our previous proof. Or we can plot alpha and beta there, where again, this is the function of Q to simplify things. Okay. So for the simple network, you have this bound. What we want to show is that this bound still holds for general network, replacing capital S by alpha G of that G or beta G of that general network. So this is one of the main theorems of the paper. And again, this is for finite size systems. So if you have a load balancing process that is ergodic, or some graph with some bipartite graph with some arrival rates and service rates, and we assume that the service rates are bounded below by some lambda 0, and the arrival rates are bounded below, and the service rates are bounded above value 0. But this is not a strong assumption. I don't know why Gio wrote it like this way. I discussed with him. Because this is a finite size system. So this minimum will always have a minimum, proper minimum. We are only assuming that it's not 0. But if it's 0, then that dispatcher doesn't count. So because it has no arrivals. Okay, so these are not strong assumptions. It's just a name on the bound. What is the minimum arrival rate and what is the maximum service rate of the system? And we call the load the ratio of the minimum arrival rate and the maximum service rate. Okay. So when you reach steady state, then you will have a geometric tail replacing the size of the graph in the previous case by this metric alpha G that we included. This is the main result. And of course, there is a slightly similar result for beta G. This is slightly more complicated, more involved. The proof is more involved. I won't be covering it here. But it looks similar. So you have to throw a +1 here. That is very annoying in the proof. We would like to generalize without the +1. And this changes a bit the constant. But it doesn't change the nature of things. You need beta G to be high in order for this to be a fast decay. Okay. So the main message of the talk is this: you can prove that you have a geometric tail for any network, and this is controlled by the bottleneck measure that we introduced. Okay, this is the main result. Of course, what this implies, if you have geometric tails, and you have now a sequence of bipartite graphs that grows, and these alpha G and beta G converge to finite limits, then these bounds won't disappear in the limit. Okay? So going back to this bound, if this has a limit, this function is continuous, this has a limit, then the bound won't disappear in the large spaces. Okay? So in order to have enough flexibility to recover the properties of join the shortest queue in a fully connected graph, you need alpha G to go to infinity. Okay? That's necessary, and that's one of the things that we want to cover. So, what are necessary conditions for having good results or good behavior? So this is daunting to look at, but what it's saying is, in plain terms, is if you have a sequence of networks, then in the limit, the tail of the occupancy will be greater than the worst of those two bounds that I showed you before. Okay, either the alpha bound or the beta bound. Okay, whatever is worse, because they are all both are low bound. Okay. So since this is geometric in nature, if this has a limit, then you have geometric behavior. If this has a finite limit, you have geometric behavior. And in this sense, so the proof is simply what I just said. So take the limit, and the bounds do not disappear, converge to a proper geometric limit. So this is what I was saying before. If either alpha or beta are finite, then the mean steady state occupancy cannot decay faster than geometrically in the limit. And this in particular is a partial converse of the results of the Van curve particular, that say, okay, if I have these assumptions, then you have, it's like you have full connectivity. Well, okay, in particular, they assume that all of the connectivity assumptions imply that beta equals infinity, implies that the average degree goes to infinity. Okay, so in this sense, it's a partial converse. If you don't have this, you will have a geometric decay. Okay? So this is conclusion. It implies that such mean field limits are not possible if the average degree of the graph, this is a corollary of the theorem. If the average degree of the graph of the dispatcher does not grow to infinity, then you cannot have the mean field limit of general shortest. Okay. So some words about how to prove this, because I think these are nice ideas before the final remarks. So how do you prove that any network will have the same behavior as simple networks? Well, the key idea here is to decompose the graph into simple networks by disconnecting things. But these transformations have to be monotone in the sense that each time you transform your graph, you get a system that is less congested than the previous in order to get a lower mark. Okay, and this is what we call monotone transformations. So you make a sequence of these monotone transformations that preserve order. Each step has better performance, and you prove that in the last step you end up with simple networks that have geometric depth. Okay, so your original system must be worse than that, so you have the geometric path. And this has to be done very cleverly. You have to couple the server departure process in order to have these monotonicity properties. But so it has to be done cleverly, but you end up with a series of parallel. You begin with a general graph, bipartite graph, and you start to split it apart in order to get for each dispatcher its own set of servers. Okay, and the degree of the dispatcher does not change. It has the same number of servers as before. The only thing is that this number of servers now are in different, not connected to the other dispatchers, but they are coupled among them in the departure process in order to keep monotonous. Okay, so you end up with capital D simple networks, and in these simple networks you can apply the previous bounds, and then you get the theorem. So what are our monotone transformations? Well, the first two are very stupid. It's just decrease the error rate or increase the service rate. These are just to, you don't have to deal with heterogeneity in the error rates and service rates. So if you increase the error rate of every node, you get you decrease you decrease the arrival rate of some node, of every node, then you get better performance because it's less congested. So this is stupid, but it's in order to not to deal with heterogeneity. This is the other one, increase the arrival rate of the servers, then your system will perform better. So this is clear that if you do a transformation from a graph or from a network 1 to a network 2 that has less arrival rate or more service rate, then the second one will be less congested. Okay? Instead, these are the stupid transformations. The interesting transformation is the edge simplification, which requires the coupling of some servers. And we need to keep track of these couplings. So start with some graph and some rates. And we'll have a partition of servers that are coupled between them. And the initial partition is each server is independent. They are not coupled. And what we will do is, I will make the drawing easier. The idea is, what the transformation is, you keep the same dispatchers, you add a new server, and you remove the compatibility between dispatcher D and server U, and you add the compatibility between dispatcher D and server B. So you choose a dispatcher, and you add a new server for him, and remove the old compatibility. So, but this server is like a copy of the previous server. It's better understood in a drawing. So what I'm trying to do here is, you start with the following network, it's simple bipartite graph. I want to split it up. Okay, so I will generate a new node for this part of the graph, and this node U is the same for the original server, for instance. But I have to couple the departure process of these two in order to keep monotonicity. Okay, so these two remain coupled. They have the same Poisson clock telling me when departures will occur. That's a coupling idea. Okay, and of course they have the same rate, but they end up being in different neighborhoods. So from the point of view of this dispatcher, this is just a server. He doesn't know that it's coupled with someone else. Okay, so the distribution of this side doesn't change by this transformation. Okay, and performance improves. So this is what we say, the servers have the same potential departure process. This is the coupling. The same Poisson clock telling me, or exponential clock telling me when departures may occur, if there is any task in the server at that moment. Okay. So that gives monotonicity. So if you do this, the server that you add is less congested than the older server. And in particular, all the other ones are better off. More likely equal. Okay. The one that will be better off will be the one that you split. In fact, like here, he will be better off because he doesn't get the new tasks from the other dispatch. Okay. So he will be better off. He will be better off even if they are coupled. So the whole network will behave better. So that's it. These are the three key transformations. So how you prove the theorem? I want to include some proof sketch or something to show you the ideas. So let's recall the bound that I want to prove. I want to prove this bound for the state of occupancy of the network. What I will try to do is to perform edge simplification at all the edges sequentially. Okay, it's a bit too much, but the idea is apply this and split apart everything until you get a simple network for each dispatcher. Okay, that's the key idea. It's difficult to write in a slide, but the key idea is if you have 20 dispatchers and they are connected, split until you have enough copies that every dispatcher is in its own simple. Okay, That's the first step. And the coupled departure processes end up being in different regions of the network. Okay, they never share the same dispatcher. Okay, because when you duplicate, you are giving one new server to each dispatcher. Okay, so you end up with a final network, which is simply capital D simple networks in parallel. Okay. Then, so this is the first step. Split it up, to have capital D simple networks. Then move all the rates so they are equal. Decrease them to the arrival rates to lambda 0 and increase all the service rates to mu 0 in order to make bounds easier to work with. And we call X0 the load balancing process that you end up. Okay. So for that process X0, which is the load balancing process of this parallel simple networks, the occupation in the original network will be larger. The probability that you be more congested than I in the original network will be larger than the server that represents you in the new network. That's the idea. Your representative in the new network is more congested than I. Okay. This is monotonicity of it. So UD is the representative of you in the final. Okay. In the neighborhood of the dispatcher. So you have this bound because of monotonicity. Now you have to work with this bound a bit. The way to do this is a trick. This is a mathematical trick. There's no intuition about it. No, Diego came up with this mathematical trick and it works. So let's do this. Let's put some weights on the edges on the connectivity of the original graph. Call that theta du. So it's a weight between dispatcher and server. But you assume that all the weights sum to 1 across the neighborhood, across all of the dispatchers that are connected to a server. Okay? So, this, so you have this server here. You see that it's connected to several dispatchers. So let's split this into a convex combination. Okay, theta 1, theta 2, theta 3, that sums up to 1. Okay, that's what theta is doing. Okay. So the expected value of Qi, which is simply by definition this sum, 1 of capital S sum of the expected value of the indicator functions, is greater than, forget all this for a moment, it's greater than this because of the previous inequality, but it's also greater than any convex combination of these things. Okay, because it's greater than any of the, any one of those. Okay, so when you make a convex combination of them, you end up having a lower value. Okay, that's a trick. It's difficult to convey because it's a trick. Let's put some weights and this works this way. But the thing is, you end up having here a simple load balancing process. So now you have a bound for this. Okay, because these are X0 are simple load balancing processes. Okay, so you use the bound for this for single load balancing processes, and the bound is R of rho 0 degree of D, because when you split up the network in several parts, several servers, okay, it was connected here, you split it up, you put it here, but the degree of the dispatcher remains constant. Okay, So if the degree of the dispatcher remains constant, the size of this simple network, the total size of the simple network is the degree of the dispatcher in the original network. Okay. So I'm using the alpha of the little simple network that I arrived to, okay, which is the degree of the dispatcher. And why we choose these weights? Why we chose these weights? Because this function it ends up being complex and decreasing in this region. And you can prove that you're always in this region. Yeah, that's easy. So you can, this is a large complex combination. Okay. So the sum over the neighborhood of u is sums to 1. If you average that over all the servers, it will add to 1 also. So you have a huge complex combination, and you have a complex function. You can use Jensen's inequality to plug that inside and average the degrees by the thetas. Okay, so that's why it's strict. Okay, so you end up, you can put everything that is summing over there inside averaging over the degree, because you are averaging against a complex function. So this is theta g. It's just the average over all the thetas of the degrees. And it turns out that the highest value that this can take is when you take the complex combination, that is exactly alpha g. Okay, so what you do is you choose the edge with the minimum degree. Okay, and this will give you the lowest value, the largest value of the map. Okay, because it's decreasing. I have to check that. So yes, this alpha g is just one pick of the theta g's. Okay, if you pick the correct weights there in the thetas, then you end up with alpha. In fact, it's the best bound that you can get using soup over all the complex combinations. So the alpha g is the better bound that you can get using this technique. That's it. So that's the idea of the proof. It's a bit long, I know, but I wanted to at least convey the way of thinking in these terms or in these types of networks. Of course, there's a lot more to be done. But if you want to conclude, what are the final remarks? Simple load balancing networks of finite size will always have geometric tails. So we define two flexibility metrics that if they do not diverge, then you have limited connectivity, you have bottlenecks, and then you won't have this doubly exponential decay or even the shortest queue, because you are not flexible enough, you know, to make things wash out in the limit. Okay. So what I think it's good for future work is to characterize the size of the bottleneck set. So instead of defining the average over all the network of alpha g, I think it makes sense to make the average for some subset of servers. Okay. And when this average for some subset of servers is low, then this subset of servers is a bottleneck for them. And if the size of this set grows as the network grows, we're in trouble. So instead of looking at the average over all the possible, the average, let's say, importance of the nodes, let's look at the set that is most important. I think that would be the next step, and try to characterize properties in, I don't know, random graphs or something, with random connectivity or something. So that's it. I hope you find it interesting. Let's see. And I'm ready to take some questions if you like.
Cool. Questions for Andrés?
Yeah. I have a very general question, because I'm sorry, I'm not sure I understood the model at the beginning, but that's my fault, clearly. I'm very rusty with queuing networks. So. But you you started mentioning that the issue is that there are some loads that can be treated only on a subset of the servers, right? Because you have some specificities. But then you look at the total load arriving to each D, right? Dispatcher. You are not differentiating among different types of loads.
Well, you can model that by duplicating the dispatcher. So you can think the dispatcher as some type of task that is associated to some server.
Okay.
So you can split that up between server and dispatcher. You have two types of tasks this can be sent only there, this can be sent over there. Then you can think that there are two dispatchers, each one with its own arrival stream.
I understand. So you have a tree that is fixed per type of a task for all the servers that can serve this type of task,
Exactly.
right?
Yeah.
Now, once you said that, that's very interesting. Now, based on this, is there any way to apply these results to the planning of the system? Means, for example, to deciding whether to position each type of processing?
Yeah, exactly. I think that that's why we think of this bottleneck set or whatever. I understand that these are really theoretical results, and Diego is very good at theory. But if you want to go to performance analysis or system design, what this is saying is you should keep track at least of the average degree or the average number of options that you have for each dispatcher. Otherwise, you will have some part of it will become concerned. So you have to keep flexibility in mind in order to design your system when the system goes on. Okay? And in particular, for the result, it's not only the routing policy that matter. You can use poverty, you can use skew, join the other queue, but it's also how well connected. So you have to be, in the case of the bank results, have to be homogeneous in your connectivity, and you have to have a lot of options. I would like to know whether that's completely necessary or having a few options, or how does that scale in some sense? How do you have to scale the number of options in our system? Is it linear in the size of the system? Is it less than linear and you're well off? That would be a good question. If it's finite, I think it would be geometric, but maybe there's something in between. That's for system planning, that would be interesting to say. Okay, you don't need to have a linear number of possible servers as your system grows large, because this gets large also. If you have square root or log n or whatever, finite won't work. That's one conclusion of this. But if you have square root of n or something, you can do better. That's an open question.
Thank you.
Other question.
Yeah, Andrés.
So you based all the analysis and the proofs, if I understood correctly, because on join the shortest queue.
Yeah.
Actually, because you said it's the best thing we can do with when n goes to infinite. So if we get results for that, all other policies will work not better than that.
Yeah.
Is it correct? Okay. But join the shortest queue, is it also the best thing we can do, even in a complex networks where the connectivity is not full, etc., etc.?
That's a good question. I think Diego may be able to answer that one. So
okay,
because he knows well all the literature. We know that it's optimal for simple networks. It's an old result. I've never seen myself a paper saying it's also optimal for bipartite graph in the finite case, let's say. For a given bipartite graph, the optimal thing it should be, but I'm not sure.
So maybe these bounds are not valid if you find a better policy for networks. No, maybe you can do better than geometric.
When the shortest queue is not the optimal policy, then you cannot apply these bounds directly in finite size. You're right.
Okay.
Because we are assuming joint short skew. That's right.
Okay.
But you can apply the bound for the simple network.
Yes.
Because there is, and the
we did
proof
it.
is based on simple network. So maybe
Okay. Okay.
the proof program will work anyway,
Okay.
even if you're using another point.
Okay.
But that it's open. I understand your question. This is for joint short skew. I'm not claiming that power of T. I'm assuming that that will be the case, but this doesn't prove that power of T has geometric tails in this. It's not a proof of it. That's good.
There is another question from the southern hemisphere.
Nahuel.
Nahuel has a question.
Hi, thank you. Yeah, I saw you wrote when you talked about the stability region, you wrote sufficient condition. I mean, the necessary condition is not known.
Yeah, it's known. It's known. I just put the sufficient condition because I will work with the ergodic systems. But it's as usual. If you have the greater than there is some part of the network that will explode. So if one of these inequalities is greater than, instead of strictly greater than, then that part of that subset of servers will explode. The queue of that subset of servers will be unstable. The problem is in the border as usual. When you have equality in one of them, then you have recurrence, things like that. So you cannot call this necessary insufficient because of the frontier. We don't know what happens on the frontier, but it's for any practical case, it's necessary insufficient.
And what paper from Sergey you were referring to?
Yeah, well, I put the talk on my page. The link is there, so it's there.
Okay, where? I didn't.
The second one here.
Ah, yeah.
My mouse wasn't working properly.
Okay.
That's why I didn't use it. Point. I know why it has a lag on the screen.
Thanks.
I have one question also. So, I mean, people look essentially at these problems at in a sense, you should, if you know more on the system, namely, for instance, the load rather than the number of customers, and if you would have, for instance, service times which are heavy tails, right? So, I mean, you might hope in view of the mean field. I don't know whether this case was studied.
The expert on that is Sasha Stolia.
Stolia, I see. And so, can you change the, because I mean, in the steady state, you know that you get, if the steady state exists, one more, if this Pareto or something like that, the exponent is changed by 1 unit, right? In the steady state with respect to the service times. But so can one expect to change some of this or to design scheduling for zip for Pareto or things like that?
You mean in the service time, not in the connectivity?
Yes. Well, of course. I mean, the first question would be just even in the power of D or whatever, as you called it, or the supermarket or things like that. Whether one, were there extensions, or is there a theory for the heavy tail case as well?
Okay, but you mean heavy tail in the distribution of in the size of the jobs?
Size of the jobs, and of course,
Yeah,
I mean,
Sasha Stolia has a paper talking
Ah.
about
okay.
I think it's from showing the short skew, not for power of D. But the expert on that is Sasha Stolia, and there are some results
I see.
on when it works. So that I don't remember the hypothesis.
And you change the order again at least in the mean field. You change the order of the tails.
I don't remember.
I don't remember.
But definitely, you should look at Sasha.
Okay. Thank you. Any comment, question? Yes.
I think that it's not really related to not related with your talk. Our community has been working for tens of years on scheduling, load balancing, and things of that sort. this morning we were in at Nokia and we heard a talk about using artificial intelligence to optimize scheduling, and they managed to have a 50% better than the better algorithms that we could imagine historically. Do you think that AI may be relevant for a load balancing as well? I'm sorry to speak about AI. I mean, as everyone does.
The thing is there a fair comparison? Because when they say I have a AI algorithm that can optimize my load balancing and it works great for this system, aren't you overfitting for your system? Aren't you fitting this load balancing technique for this particular system? And these are general load balancing. They work for any network. Okay, so it's not a fair comparison. Okay, if you optimize the load balancing or how you do your load balancing for your traffic with your given network, and you optimize it using, I don't know, whatever, classical optimization tools or artificial intelligence, but you optimize for a particular network, then the comparison is not fair against a general algorithm that works in a general setting. So I think both things are needed. If you have a real network, why don't you try to optimize it with all the tools you have? I'm not against AI in this setting, okay? But the thing is, if you want to have general results, if you have intuition on what's important, for instance, your first question, how important is
design,
the flexibility of the servers? AI won't tell you that. Okay? So you need fundamental results to tell you that. And so you need both. You know?
That's the reason why the question about design, because planning. Because if it is for performance evaluation of a system that is well established, as you said, today it's difficult to compete against AI, even with the best models. But if you need to design the system, to design where to locate such or such a functionality,
or at least to even to give the AI the constraints. I mean, I want to. You can ask ChatGPT like that. Design me a geographical load balancing network, but you have to tell. But I need this flexibility. So that comes from the fundamental result. And then maybe if you keep the machine, the AI will optimize everything and leave you bipartite graph that's flexible enough and whatever. Okay. But if you don't realize that you need that flexibility, you're not asking the right question.
correct.
Biasing and doesn't have information to give you a new solution. That's the way I see it.
It's just for the younger, for the PhDs in the room. I was not trying to say that this is not useful. On the contrary, I wanted you to highlight why it is.
No, I said it. I mean, I think fundamental results are important because they highlight the things that are needed in the design or in the performance model. Then, if AI guys fit to some particular example, that's great. Related to that, I mean, I learned this from Francois a long time ago. When Francois was teaching stochastic geometry, I think I asked the question at one point. The teaching stochastic geometry, he was doing this with you, Daniel, about placing base stations near to users, and the process of base stations is random. And why random? Because the base stations are in some place. Okay, so it's not random. It's a given network. But if you do, and this is your argument, if you understand what happens on a random network, you understand what happens on any network. You have a fundamental result. Then you can go, you have your base stations located at this hill, this hill, this hill, this high point, this building. And then you optimize that one. But you learn something fundamental by looking at the average over all the possible networks. That I learned from you. And I think it's a very nice argument of why fundamental results are needed.
Thank you very much.
Thanks.